Hi, this is Andreea. This talk is about data race repair using static analysis summaries. It is a collaboration work between Abhishek, Abik, Ilya, and I. First, let's see what races are. In the wild, races occur when two entities compete for the same resource with no proper supervision. For data races in computer science, though, things are a little bit more complicated. To set the stage for our motivational case study, let us consider an example consisting of two classes. One, to query and update an account by getting and setting its balance field, and the other one, which acts more like a wallet with support for asset withdrawal and deposits through indirect reads and writes to the balance field in the account object. The issue with this program is that two threads may very well execute withdraw concurrently, causing inconsistent read and write interleaving, and possibly leading to application-specific bugs such as double spans. Now, the even more subtle bug here, though, is that two accesses may race on the same memory location, possibly causing serious memory corruption or memory leak and not just inconsistent balance. In a nutshell, a data race is defined as two concurrent accesses to the same resource where at least one is a write. Let us next see how to detect and repair data races. The most commonly used method for data race detection is through dynamic analysis. Dynamic approaches traverse through the most visited execution paths of a program and check only those resources which are used in the current execution of the program. Though incomplete, this method generally detects bugs that are true bugs. In contrast, static approaches aim to consider all possible execution traces, thus considering for all possible thread interleavings and uncovering all the possible bugs. Though complete in the ideal scenario, it generally suffers from many false positives. There are few efforts in automatic program repair for data races, with pfix being the most recent concurrency bug fixing tool for Java programs, shown to significantly outperform the previous state of the art, namely Grail, in terms of efficiency, correctness, and patch quality. pfix is actually more of a hybrid approach, since its key idea is to systematically fix concurrency bugs by dynamically inferring locking policies from failure-inducing memory access patterns discovered through model checking. So although the bug detection suffers from less bug misses than those dynamic analysis based on user-provided test cases, its dynamic component still incurs overheads and scalability issues because of the need of storing too much contextual information during execution time. Thus far, pfix can only handle micro benchmarks. Another drawback is that the JPF model checker used by pfix for bug finding requires user-provided temporal properties, a requirement which makes such an approach difficult to be generally adopted. To summarize, if we consider the set of all true data races, dynamic-based approaches will only fix a subset, while static analysis generally aims too high, hitting too many false positives, and thus constraining the kind of fixes they can actually handle. For example, Grail aims to fix large-scale projects, but suffers greatly in performance, and it fails to consider bugs which span across multiple classes or methods. What we would like to do is to hit the sweet spot somewhere in the middle, where we can fix more bugs than dynamic-based approaches without serious performance overheads, while finding most, probably not all, of the true bugs and actually fixing them. To this purpose, we looked into existing static analysis-based race detectors and found a suitable candidate in RacerD, a data race detector used at Facebook, which has been shown in practice to have a high signal, scalable, scales for very large code, and it's modular too. Equipped this way, we make it our goal to fix true data races at scale while minimizing the adoption effort. To this purpose, we introduced HIPPODROME, a data race repair tool which uses static analysis summaries to produce program patches. Let's see next what sort of information do we need to collect in order to detect and fix a data race. Given the data race definition, we will summarize individual program components such as method and classes by set of access descriptions of all resources in the considered component. An access description or an access snapshot is a tuple where we capture the resource as a syntactic access path, which is a base variable followed by a sequence of fields, along with its resource location. We also capture an indicator to denote whether it's a read or a write access. L is the set of mutexes which protect the current access. T, detect mutual exclusion due to running on the same thread. The key feature of this domain is determining whether an access must occur on a thread that runs concurrently with other threads. O detects mutual exclusion owing to memory that is held exclusively by one thread and thus not shared between other threads. And finally, tau is the trace to the resource denoted by pi, and it is non-empty for indirect access. Having collected such information about all resource accesses, we can then confidently detect a race between any two accesses if two snapshots refer to the same syntactic path, at least one is a write access, they are protected by disjoint locks, they can be executed from threads running concurrently, and both accesses refer to memory that is shared. An unprotected write, which is a special case of a data race, is one where a write access is not protected by any lock. It's executed from a thread which may run concurrently with any other thread, and its resource is not owned. In our running example, the withdraw method is summarized by a set of two accesses, where one corresponds to retrieving the balance by indirectly reading the value stored in the shared field of the account object, while the other accesses an indirect write access to the same field. These accesses contain sufficient information to point to both a data race between the access at line 22 and the one at line 24, as well as an unprotected write at line 24. Although such a summary contains valuable information with respect to the existing data race bugs, it is still not clear how to fix it. What lock should we use? Where should we place these locks? And then which statements should be protected? Are the statements in customer info that need protection or those in account? These sort of questions are addressed in our framework. HIPPODROME takes Java programs as input, analyzes them for data races, and stores this collected information as access summaries and bug reports. The access summaries and bugs collected from the analysis are then merged into a set of bugs, which is then clustered to support fixes across multiple related bugs. I will shortly talk a little bit more about this clustering. We design a series of small domain-specific language to first encode the generated patches and to then compile them to AST transformations before finally applying them to the input file. The patches are validated by the analysis for the absence of deadlocks until no more alarms are raised, in which case the bug is considered fixed and the patch is automatically applied. Everything is done automatically with no user effort. Our framework also works interactively where a set of fully validated patches are suggested to the user via an IDE. An initial investigation on large projects showed that it generally suffices to generate patches using only synchronized blocks and volatile annotations. Hence, we limit the solution space to patches containing these two constructs. Consider next three possible concurrent accesses to the same resource pi. Access A2 and A3 are protected by locks, but these locks are different, hence they may still race with each other. Actually, any two accesses in this scenario may race with each other. If we were to attempt to fix each pair of bugs individually, we might end up with too many locks. Clearly, this pseudo-fix is problematic, not only due to the clutter of synchronizations, but also because it naively introduces a deadlock as highlighted by the dashed arrow. To improve patch quality, instead of deriving patches from individual bugs, we will infer them from bug clusters. We will do so by analyzing sets instead of pairs of snapshots, grouping bugs according to their shared access paths. This gives us a holistic view of the bugs. And now that we decided on this holistic view, we should choose a lock. For this, we opted for a simple yet efficient solution, which leads to easier to maintain code. We choose the lock most commonly used in the consider bug cluster, if one exists. Else, we create a new one, carefully considering the scope in which it will be used. Let's now go back for a moment to our motivating example and consider the deposit method as well, where the diligent programmer already fixed the atomicity issue by creating atomic withdrawal and deposit actions. Although atomicity is fixed, there is still an issue. Withdrawal and deposit might be executed concurrently, hence interfering with each other's view of the balance. We could generate yet another lock to govern over both methods and then do so for any other method call that for any other methods that call setBalance and getBalance, or we could dig a little bit deeper into this issue, and instead of fixing the bug where it manifests, we could fix it at its source, namely protect all the accesses to the balance field from the account class itself. For this, we inspect all the call chains of the bugs in a cluster and choose to protect accesses at the innermost call context common to all bugs in the cluster. Now, there are a few other subtleties I will only briefly mention, such as merging neighboring synchronization blocks in order to avoid performance overhead due to too many context switching. Also, there are also situations where we need to carefully handle the scope of the variables caught in the middle of a synchronization while making sure that the semantic of the program doesn't change. Care must also be taken when HIPPODROME singles out volatile annotations from context where a single declaration statement contains multiple variables, or to carefully handle the scope when dealing with nested classes. We evaluated our approach to find out how does HIPPODROME compare to the state-of-the-art repair tools in terms of performance and efficacy. We chose 24 unique applications from the benchmark suites universally adopted by the automated program repair community as a baseline for evaluating tools for fixing concurrency bugs. We chose these subjects with two aims. One is to evaluate HIPPODROME on a variety of data race patterns, and the other one is to include all the subjects from the PFIX suite, thus comparing PFIX on its home turf. In measuring the performance of Hippodrome, we distinguish between detection time and fixed time. And in all cases, Hippodrome outperformed the state of the art. Furthermore, a manual inspection revealed that the quality of the patches generated by Hippodrome are the same or better in quality than those generated by PFIX. We also evaluated Hippodrome with respect to its performance on large projects, and in order also to find out how do the patches it produces compare to developers' manual fixes in terms of quality. For this purpose, we cloned Apache Tomcat and Google Guava, investigated their commit history for data races, raised issues, and ran Hippodrome on them. We analyzed 50 concurrency bugs, and the analysis successfully reported 39 of those. Hippodrome repairs 31 out of the 39 concurrency bugs. Repairs for 18 bugs were syntactically the same as the developer fixes. And actually, in 2 cases, Hippodrome generated better repairs, introducing less overhead. Overall, Hippodrome runtime performance scales very well for a large project with roughly less than 80 seconds per bug from starting from a cold setup. And of course, our approach doesn't come without limitations or future works. We currently support no fine-grained logs, as I mentioned, just synchronized blocks, which are more coarse-grained. We have a limited atomicity support, where we only merge neighboring synchronized blocks. And we currently only experimented with a simple cost function, where a fix is cheaper if it's syntactically less intrusive. Hippodrome also suffers, may also miss deadlocks when the locking code is in line in the spawn threads, and suffers false positive when a local object is linked to another thread. To conclude, we have presented Hippodrome, which harnesses static analysis for concurrency bug detection, and shown how to reach from static derived summaries of programs to program patches for data races. We have also shown how bug clustering leads to patches of better quality, while outperforming the state of the art, both in terms of time and quality for micro benchmarks. We believe that the performance of Hippodrome makes it a good fit for a continuous integration loop. The tool is open source or can be downloaded as a Docker file where it can be tried out as an extension to IntelliJ. Yep, that is all. Thank you for listening.
Thank you, Andrea, for the great presentations. And we are moving to the Q&A sessions. Please, anyone, if you have any questions, please type in the Zoom chat and we will be having the Q&A. Hi, Andrea. I hope you're doing okay.
Hi, yes, all good. Thank you. Thanks for helping to organize this great event. Really pleasant.
Thank you for your willingness to participate. It's a great talk and great interesting topic as well as for the bug detection. So how specialized is the tool to raise RD? Could it be generalized to other race detection tools? There's a question from the audience.
Oh, yeah, that's a very good question. So actually, when we started to work on this problem, the only game in town that we could actually use was RacerD. So although initially we kind of fine-tuned a little bit to RacerD's abstract domain, we realized subsequently that actually this is just a constraint. This is the information that we need. So as long as there's a tool which is modular enough and collects the minimum information we need in order to reproduce, produce a patch, that shouldn't be necessarily a problem in terms a theoretical problem, but just an engineering problem, just fine-tuning the output of another data race detection to Hippodrome.
Okay. Yeah, someone said we wish he had this tool before, like a decade ago. So yeah. Okay,
thanks,
so
to add to that, I was working in industry like 10 years ago, and oh my God, the number of synchronization bugs. But I came in a little bit late. Have you covered how you tell the difference between pairs of accesses that are always in the same thread versus, even if they're in different locations of the code, versus ones that'll be perhaps in the same class, but could be from different threads?
Yes, so actually this is courtesy to RacerD detection mechanism, which is able to infer whether a certain instruction is executed from a thread which will run concurrently with other threads, or it will always be non-concurrent executions or a sequential execution. So that's actually quite a meaningful information which can be collected statically based on analysis of keywords and certain user annotations. So keywords that RacerD searches for are like checking for thread spawns or locks. There is an annotation called thread safe. So if a class is annotated with thread safe, then it's considered that that should be analyzed, because it will most probably run concurrently with other threads. And yeah, so the user effort is almost zero in this case. The thread safe annotation is not mandatory given the analysis of the code for keywords like synchronized and yeah, so on. And yes, I agree with you, the fact that these tools, such kind of tools would be really useful in industry. So I read a report where it says that given a bug report during compile time, the user is more like 70% more likely to fix the bug versus 0 to 20% if the bug report is provided during checked in code, so after commit and all that. So yeah, lots of bugs are actually not fixed and stay in the pipeline just because the feedback is given too late.
Oh, it's not even that. Like we got all kinds of crazy bugs that had to be fixed. These were like priority maximum bugs that were just going to completely kill a product in front of the user, but we couldn't figure out why it was happening.
Yes, correct. Yes, that's certainly a very tricky point. So when you have an automated tool that just says, you know what, just insert a synchronize here and here and the data races. Well, if you have to manually analyze thousands of lines of code to discover this nitty-gritty of data races, then yeah, it's.
I was actually going to suggest what you were talking about, whether in terms of code quality, this is one where I think you can get like a Pareto principle on it, where if the code quality is even 80 or 90% there, if you present it to a developer and say, here is, potential fix, they can look and go, oh, that's where it is. And even if they change what the synchronization element is, if you've got it 80% of the way there, oh my goodness, that makes life so much easier.
Thank you for the support, Karim.
Okay, thank you. But I think I have to spoil your fun in discussing this because we are within this time boundary. So because we are having the next session very soon. So thank you so much, Andreea, and also Karim, for the discussion. And maybe we can continue in offline or beyond this event for sure. Okay, thank you very much. And we will be proceeding with the next one. See you. Bye-bye, Andreea. Thank you.
Bye.